Right, okay, so calculus. So calculus is a big umbrella topic. So you will have looked at differentiation, as I said last year, well, for GCSE. Within calculus, there's differentiation and there's integration. Now, we're not going to look at integration until later on in IB2, but those two processes are the opposites of each other. Okay? So when we're asked to differentiate something, we're asked to find the gradient of a straight line. No, shut up. Differentiate and talk about gradients, okay? Start again. If we're asked to find the gradient of a straight line, we know it's the same, yes? We just find 2 points, rise and run, lovely job, yes? It's going to be the same all the time. If we're asked to find the gradient of curves, they have to be more specific. They have to say, find the gradient at this point, at this point, at this point, at this point, okay? Because it changes. Oh, shush now. Because it changes all the time. Yes? Makes sense? Yeah. Okay. Yeah. If we wanted to find, and I've just moved it so I don't know where it's supposed to go. Let's take this. Oh no, this is, let's go. Shut up. Oh my god. Right there. And this is our video.
We just restart the whole
thing. Right. If I wanted to know, so these are along here are my x values, yes? So if I had been asked to find the gradient of the graph at the point where x equals -1, yes, I would find the value of -1 on my x-axis. I would go up to my graph, which is there. I would draw a tangent to it, yes, and I would then find my rise over my value. Okay, and that would give me the gradient at the point where x is -1. If I wanted to find when x is 2, I would do the same thing. I'd find the value of 2, I would draw a tangent, I would find my rise over my run, I would be able to take what the gradient is.
See how you're drawing a tangent like that, right?
Yeah.
And then you're drawing the bottom of the triangle like where the tangent stops.
Yeah.
Are you supposed to draw it at a specific length?
No.
So wherever it
yes.
It doesn't matter.
Yeah, and that goes back to the straight line ones, because it didn't matter how long this line was it? As long as we found any 2 points, you could find the rise and run. It should always simplify to be the same answer, okay? Now, the issue with doing that is it's only going to be approximate, because drawing tangents is really hard, okay? Yes, they're lines that just touch, but Shannon's tangent may be slightly different to Malai's, maybe, which also might be different to oh my god, that was hard to say together, to Mia's, because it's just not very accurate. It's also more challenging to do because you've got to take your scale into consideration. Okay, so you're not just going to measure the centimetres of it, you've got to look at the scale of that as well. So this, not great method of doing. Okay, so what we want to do is find an easier way of doing it. If we can find the derivative of the function, that allows us to find an exact value of that gradient at specific values of x. Okay? So, what have I said here? I'm sure it's very useful. Draw tangents, very tedious. Yeah, so we need to find a way. We would use calculus. Okay, so our calculus expression, it's a derivative. Okay, so that's this word here. So we differentiate something. We end up with the derivative. And that's an expression that involves x, usually. Okay, so that as an expression. So if I want to find it at a particular value for x, I then substitute that in and get an answer. Okay? Someone says what?
Okay, that's
What do you mean?
everything.
Oh, shit.
Yesterday, where you take the number and you do that.
But yes. So now,
It's not quite
no, it is the second bit, the actual derivatives, yes. So now, we talked about this yesterday, what's the rule for differentiating something? How do we differentiate?
You gotta do that thing. Yeah.
How do we do? What's the power? Where's the power go?
Top right. I love my
Oh, exactly.
Power goes to the front and subtract 1 from the power. Okay? Now I do it in like just layman's terms, literally, because that's how I remember it. Now there are fancy pants ways of writing it, but quite frankly, I just would rather know that. So if I've got y equals x cubed, following this rule, what's my derivative going to be?
3xy.
Okay, it's not going to be, now this time it's not going to be y equals, okay? So it would be 3x squared, because my power has gone to the front, and I've taken one off. But we wouldn't call it y, okay? Because y
is
refers to the function.
and it cannot be
Correct, okay? So if y is x cubed, then it also cannot be 3x squared, yes?
Two different things.
So, what do we call it? Well, we would write dy dx. Okay, so this is fancy terminology. So if your expression was y equals something, to show that you've differentiated it, you would write dy dx.
Are we reading out there?
dy dx. This said dy by dx. Now, if I had written fx equals x cubed, my derivative would still be the same. The power still comes in the front, take one off the power. But I would show that it's the derivative by writing f dash x. So I would say f dash x would be 3x squared. Okay? So please don't get stressed about what the real difference is. Just sometimes we write things as y equals, sometimes we write them as fx. Okay? And just to show that you've differentiated it is where the apostrophe comes in. Now, this is where, do you remember we were looking at inverse functions? Okay, to show the inverse, it's f minus 1x, yes? And that's where people get confused. They get the derivatives and the inverse functions mixed up. So just please be aware that when it's an apostrophe, it's the derivative. When it's a minus 1, it's the inverse. Trace the hands. Now, if there's a coefficient, we all know that means value in front of x, then that just stays there and we multiply the power by that. So if I had y equals 3x to the power 5, I would say dy dx, because it was a y equals expression, 5 multiplied by 3x, and now my power is a 4. Yes? Now, I wouldn't leave it like that. I'd actually work out what that is. So I would say that that's 15x to the 4. Now, obviously, this step here is a side step. Okay, you don't have to show that working, because I think you're all capable of just trying to directly in your head, and you wouldn't get step mark working methods. Best marks here. Which one? I need a holiday. Right, so 15x to the power 4. Trace. If there's more than one term to an expression, you just differentiate them term by term. So I've got y equals x to the 4 minus 2x cubed plus x squared. So dy dx is going to be, what is it, people?
I concur.
4x cubed
Minus 6x to the power 2 plus 2x.
Transients. Cinchi, yes? Do we remember doing this at GCSE?
No.
Oh, okay, good. Great.
Nice. No, it's not good. Show the sound.
So 4x cubed minus 6x squared plus 2x. Alright. Now, if something has just an x, okay, so for example here we've got 8x, so there's no powers or anything. It's the derivative is going to end up just being, whatever the value is in front of it. But I want to just explain why that is. We know that 8x can be written as 8x to the power 1, yes? So following our rule, we would do 1 multiplied by 8x, and we take 1 off the power. Well, what's 1 take away from 1? 0. Okay? And then what do we know about anything to the power 0? It's not 0, it's 1. And so this now becomes just 8. Okay? And that's going to happen for anything where there's just an x. So if the x has a power, just follow the rules as normal. If it's just an x, it's going to end up just being the coefficient of it. Okay? Whether that's a half, whether it's 72, whether it's negative 16, whatever it is. As a side note, if you just had y equals x, don't forget the coefficient of that is 1. So dy dx would be 1. Okay, because some people forget.
Miss Harrison,
We.
if we can do this, why don't you do that long method?
Sometimes you have to learn.
Angel, what did I say at the beginning of yesterday's lesson?
Sometimes they ask you
To specifically show you the differentiation from constant.
Right. So doing that, you get nothing.
If in those questions, if you just wrote 8, you get nothing.
No, right. But if you did the times 1,
You would never
You would still get nothing. Because if they've asked you to use first principles, you have to use first principles. Okay? It doesn't happen very often, but as I say, it's the whole lesson for us to teach with. Alright, so for this one, my derivative would be 3. For this one, negative 5. Tracy. Now, if you're differentiating an expression and there's a constant term, so remember constant terms mean that there's no x attached to it, that constant term disappears. Okay, that constant term differentiates to be 0. So if I have this expression here, dy dx would be 15x squared, okay, and that's it. Now, a tip for you, because it's the constant ones that people often forget about. If I have forgotten that the plus 4 ends up as being 0, I would have done 15x squared minus 2 plus 4. Okay? And you then look at that and say, oh, look, hang on a minute, I can join like terms. These two join together and I get plus 2. When you differentiate something, you should never be able to join any like terms. Okay? Because these terms here are all different, which means that your derivative must have different terms. Does that make sense? Mm-hmm. So please try and use that as your guide as to whether you've done it correctly or not. Oh, and then okay. So that's that. Now, here we get interesting. The power might be negative. Okay, rule still applies. You multiply by the power, so dy dx would be negative 3x, but you've got to remember that if you're subtracting 1 from negative 3, it becomes negative 4. Okay, so that's the only thing that you need to remember. Now, what makes a power negative? Well, if it was written like this, this would indicate that actually this can be rewritten. Okay, so this is where your laws of indices come in, and we all love our laws of indices. So for questions like this, where you've got fractions involved, the first thing you need to do is rewrite the expression. So notice, this said y equals, this also says y equals, because I haven't differentiated it yet. I'm just rewriting it. So this expression here would become x to the negative 4. Okay, let's just rewrite them all first. This one here would be what? X to the negative 2. This one would be 4x to the negative 3, good. Oh, and what would this one be?
This would have to be
Yeah,
3
3x to the
the
negative 2. What is it, 3x?
Yes, Haley's got it. 1 over 3x to the negative 2. Now, the reason being is that remember, it's just the x that has its power. Okay, so it's just this thing here that is raised to the power 2. So it has to stay as 1/3. Yes, we're happy with that? We're not happy with it, but you get it? Right, so I've rewritten all my expressions, now I can differentiate them. Okay, so now they're all white. Sorry, this is pretty boring. So dy dx. So negative 4x to the negative 5, yes. Dy dx equals negative 2x to the negative 3. Dy dx equals, what's this one going to be?
This is going to have to be minus 12 x mod over.
Yeah. And what about this one? Well, we're going to do 1/3 multiply. Yes, multiply by almost. Multiply by negative 2. So it's going to be negative 2/3 x to the negative 1. Negative, not negative 1, Miss Sarah said. Negative 3. Just shift the wait. And
Yes, I was just going to say.
okay.
Okay.
So for these ones, once you've rewritten the expressions, you then have to differentiate. So our red is just rewriting it. Our green is doing the differentiation. Right. Now, alongside negative powers, what's she talking about?
So let's
At least we're on.
Along with negative indices, we also have fractional indices. Yay! We all love a good fraction. Woo! So, now this here is not great. I need to change it. This says a to the m over n. That's what that says. Doesn't really look like it though. So, base is a, and we've got to the power m over n. Now, do you remember my little tip about fractional indices? N is on the bottom. So n represents the root, because remember, roots grow in the ground. Remember that?
No.
This one? Grow in ground.
What does it have to do with n?
Because if you have a fraction that's like 2/3, it means the 3 represents the root. Like the cube root or
So it
the...
has nothing to do with the actual numbers too.
No.
I just thought like you had used n because like it gave you some hypods.
No. I would have used R for root if I had thought that far ahead. And then M is on the top, which is more powerful, and so that's a power.
That's good.
Thanks. Power. More powerful. Now, in 6 months' time, when I say this to you again, you'll go, oh, that's a good thing, yes. And I'll say, oh, I've actually told you this already. You'll say, oh, right, okay, thanks. So, for this one here, I can see that the squared sign, and then my root is a 3, so this would be a to the power 2/3, and vice versa.
Yeah.
Okay? Now, these two versions are the same. The order that you power or root things doesn't matter. So the root can be then powered, or the power can be rooted. Okay, so that order isn't important. Either way, though, it would be to the power 2/3. And you do need to be able to rewrite stuff. So if I've got this here, remember normal square roots, we don't ever write 2 in. Okay, so if it's just a square root sign, you know it's to the power 1/2. Okay, so if I was differentiating this function, I would first of all rewrite it as 3x to the half. I would then differentiate it. So this is f dash x to show I'm differentiating it. And you've got 1/2 multiplied by 3x. Now this is where your ability to subtract 1 comes in. So you've got a half and you're subtracting 1.
So go what? Hey, we have a half.
You've got a half, subtract 1 whole one. Minus 1. Yes.
Oh.
Now, I know you all love a good decimal, okay, but try and say fractions. Okay. Here we're going to need to simplify that. What's 3 lots of half? Or 3/2. Again, I would say improper, if possible.
Wait.
I'm waiting.
Oh. So if there's no power, then you have to do the 1/2 thing?
No, so if it was written like this, in order to differentiate something, it has to be written as a power. Right? So for these ones here, where they were fractions, I had to change them to be powers first. For these ones, for this one, it was a root, so I had to change it to be a power first. For the ones previous, so like it was just 4x, that would just be 4.
Okay.
Yeah? You look at me and say you're not really sure about that.
I think we should do some practice.
I'm going to do this as well. This comes up as well. Now, sometimes we have stuff like this. Okay, we're asked to differentiate this. Okay? If we have stuff like this, we are able to separate this into 2 parts. So if I've got x squared plus 5 all divided by x cubed, what I would do is I would separate that to be x squared over x cubed plus 5 over x cubed. Okay? Because that's what this means. It means that both the 2 things on the top have the same denominator. So I would separate them. I know that x squared divided by x cubed is 1 over x. I've got more on the bottom than I do on the top. Yes? Or you could say 2 take away 3 is -1, so you can go straight to this. I don't mind either way. And then 5 over x cubed will be written as 5x to the negative cube. Now once you've got this, you can then differentiate. But you need to get to that stage before you can differentiate. You can't differentiate it when it looks like this. Okay? So I'm not going to bother doing the differentiation. I'm quite sure that you're capable of doing that. But I want to show you how to do these things. So for this one, what would I write?
2x cubed over x plus x squared over x plus 5.
Yeah. And then how does that simplify?
So basically, 2x.
So I'm going to write this.
2x.
Yeah.
And then x. So
Huh? Yeah. Maddie, you're on fire.
sometimes it hurts.
Where? Why?
The x comes from
This one here.
no when you do the x squared over x.
Oh, because this is a secret one. And so this is cube 3. Well, rules of indices, you subtract powers. So this was 2 take away 1. Yeah. I know you were talking about this one, and I know I started talking on this one, but this one's easier to recognize. Yes, good. Maddie, that was excellent.
What was that?
Again, I can't bother to actually differentiate it. So the hard thing is actually getting to that. Yeah. If the expression is inside brackets, you need to. Well, no, that's fine. If it's just a squared sign, it's probably easier to expand it first and then differentiate. Okay. When these are higher powers, we're going to deal with those things later on. Oh look. Not all. See? Don't do that.
Sorry.
I thought that was
It's
a bird.
Why? All right, so
Practice.
let
I was
us
like, why is that
practice
bird?
though some questions.
What?
Practical.
Hey, the stars are getting a backwards.
One second.
Wait.